Close your eyes tonight and imagine the sun, that enormous golden sphere that warms your face each morning. It has been shining steadily for 4.5 billion years, pouring light across the solar system without pause. It feels permanent, it feels eternal, but it is not. The sun is a star, and like every star that has ever existed, it was born, it is aging, and one day it will die. This is not a tragedy. It is the natural arc of stellar life written in the laws of nuclear physics. Tonight, we will walk gently through the entire biography of our sun, from its first stirring in a cold, dark cloud of gas to its quiet final breath as a cooling white dwarf. Every stage is governed by physics that we understand in remarkable detail. The proton-proton chain, the Kelvin-Helmholtz contraction, the Chandrasekhar limit, these are the chapters of our star's story. We know when the sun was born, we know how it burns, we know how it will end. The numbers are specific, the evidence is strong, and the story is beautiful. Let it carry you gently into sleep tonight, this calm accounting of our star's long and luminous life. We begin not with fire, but with cold, with silence, with darkness. We begin in a molecular cloud, drifting quietly through the Milky Way about 4.6 billion years ago. Before the sun existed, its raw material drifted as a cold cloud of hydrogen and helium gas, laced with traces of heavier elements. This molecular cloud was vast, perhaps 50 light-years across, and extraordinarily cold, about 10 to 20 kelvins above absolute zero. At those temperatures, hydrogen atoms pair into molecules. The cloud is dark, invisible to ordinary light, detectable only by the faint glow of its dust in infrared. The density inside the cloud was not uniform. There were clumps and filaments, regions slightly denser than their surroundings. In one of those denser pockets, gravity began to win its slow battle against the gas pressure that kept the cloud spread out. Something may have triggered the collapse. Perhaps a nearby supernova sent a shockwave rippling through the cloud, compressing it just enough. Or perhaps a spiral arm of the galaxy swept through, squeezing the gas as it passed. Whatever the cause, a region of the cloud began to contract under its own gravity. This contraction is called gravitational collapse and is the first step in the birth of every star. As the gas fell inward, it did not fall straight. It spun because the original cloud had a slight rotation. Angular momentum conservation forced the collapsing gas into a flattened disk around a growing central mass. That central mass would become the sun. The surrounding disk would eventually form the planets, moons, and asteroids of our solar system. But for now, the sun was nothing more than a dense knot of gas, slowly growing warmer as gravity compressed it. This process of heating through gravitational compression is called Kelvin-Helmholtz contraction, named after Lord Kelvin and Hermann von Helmholtz. In the 19th century, Kelvin and Helmholtz proposed that the sun's heat came entirely from gravitational contraction. They calculated that this mechanism could power the sun for about 20 to 30 million years, far shorter than the billions of years geologists required. The resolution of this puzzle would not come until the 20th century, when nuclear physics revealed the true source of the sun's energy. But in the early stages of the sun's formation, Kelvin-Helmholtz contraction was indeed the primary source of energy, heating the protostar as it shrank. The collapsing cloud grew hotter and denser at its center. Over roughly 100,000 years, a protostar took shape. A protostar is not yet a star. It does not yet sustain nuclear fusion. It glows from the heat of its own compression, radiating in the infrared. The protostellar phase is violent and turbulent, with jets of material shooting outward along the rotation axis at hundreds of kilometers per second. These jets can stretch for light years, carving tunnels through the surrounding cloud. The young sun was a messy infant, surrounded by chaos and brilliance, still gathering mass from the cloud around it. As the protostar continued to contract, its surface temperature rose to about 3,000 to 4,000 kelvins. It entered a phase called the Tauri stage, named after the prototype star T Tauri in the constellation Taurus. Tauri stars are stellar toddlers. They are luminous, variable, and prone to violent outbursts. The young sun in this phase was about 2 to 3 times more luminous than it is today, even though it was not yet fusing hydrogen. Its brightness came from gravitational contraction and from the heat released as material from the surrounding disk fell onto its surface. Tauri stars have powerful magnetic fields that channel infalling gas into dramatic accretion streams. These magnetic fields also drive strong stellar winds, blowing away material from the disk and gradually clearing the space around the young star. The Sun's Tauri phase lasted roughly 10 million years, a brief childhood in stellar terms. During this time, the planets of our solar system were beginning to form in the surrounding disk. Dust grains collided and stuck together, building up into pebbles, then boulders, then planetesimals, then protoplanets. The inner disk was too hot for ices to survive, so the inner planets formed from rock and metal. Beyond a boundary called the snow line, roughly where the asteroid belt is today, water ice could condense, providing extra building material for the giant planets. Jupiter and Saturn grew massive enough to capture hydrogen and helium gas from the disk, becoming gas giants. All of this happened while the Sun was still a child, still contracting, still not yet igniting the nuclear furnace in its core. But the core temperature was climbing steadily, 10 million kelvins, 12 million, 14 million. And then about 4.6 billion years ago, the temperature and pressure at the center of the young Sun reached a critical threshold. Hydrogen nuclei, protons, began to fuse together, releasing energy according to Einstein's famous equation, E=mc². The Sun had ignited, a star was born. The fusion reaction that powers the Sun is called the proton-proton chain, or PP chain for short. It is a multi-step process in which 4 hydrogen nuclei are fused into one helium-4 nucleus, releasing energy. In the first step, 2 protons collide. One of them undergoes a transformation, converting into a neutron via the weak nuclear force. This produces a deuterium nucleus, 1 proton and 1 neutron, bound together, along with a positron and a neutrino. The positron immediately annihilates with a nearby electron, releasing a burst of gamma-ray energy. The neutrino, a ghostly particle that barely interacts with matter, escapes the Sun entirely in about 2 seconds. In the second step, the deuterium nucleus captures another proton, forming helium-3 and releasing another gamma-ray. In the third step, 2 helium-3 nuclei collide, forming helium-4 and releasing 2 protons back into the plasma. The net result is that 4 protons become 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and several gamma rays. The mass of the helium-4 nucleus is about 0.7% less than the mass of the 4 protons that created it. That missing mass has been converted into energy. This is what powers the Sun, the quiet annihilation of mass into light. Every second, the Sun converts about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons become pure energy, radiated outward as photons. This rate of fusion has been sustained for 4.5 billion years and will continue for roughly another 5 billion. The PP chain dominates in stars with core temperatures below about 17 million kelvins. For hotter, more massive stars, a different fusion cycle takes over, the CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts. In the Sun, the CNO cycle contributes only about 1.7% of the total energy output, but in stars just slightly more massive, it becomes dominant. The details of these reactions were worked out in the late 1930s by Hans Bethe, who received the Nobel Prize in Physics in 1967 for this work. Bethe showed that the Sun is a carefully balanced nuclear reactor, sustained by conditions so extreme that they exist nowhere else naturally in the solar system. The core temperature is about 15.7 million kelvins. The core pressure is about 250 billion atmospheres. The core density is about 150 grams per cubic centimeter, roughly 13 times denser than lead. Under these conditions, protons move fast enough that a tiny fraction of their collisions result in quantum tunneling through the electrostatic barrier that normally keeps them apart. Without quantum tunneling, fusion would be impossible at the Sun's core temperature, Classical physics predicts the protons are not hot enough to overcome their mutual repulsion. But quantum mechanics allows a small probability of barrier penetration, and with the enormous number of protons in the core, that small probability adds up to a steady, reliable energy source. The Sun is powered by a quantum mechanical miracle, sustained by the sheer number of particles attempting fusion each second. In the 1960s, a physicist named Raymond Davis Jr. set out to detect the neutrinos streaming from the Sun's core. He built a detector deep underground in the Homestake gold mine in Lead, South Dakota, nearly 1,500 meters below the surface. The detector was a tank containing 380,000 liters of perchloroethylene, a common dry cleaning fluid. Neutrinos from the Sun's pp chain occasionally interact with chlorine-37 atoms in the fluid, converting them to radioactive argon-37. By carefully extracting and counting the argon atoms, Davis could measure the flux of solar neutrinos reaching Earth. The experiment ran for decades, from 1970 to 1994, producing one of the most puzzling results in physics. Davis detected only about 1/3 of the neutrinos predicted by the standard solar model. This became known as the solar neutrino problem, and it persisted for over 30 years. Some physicists wondered if our model of the Sun's core was wrong. Perhaps the temperature or composition was different than expected. The resolution came not from solar physics but from particle physics. Neutrinos come in 3 types called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The Sun produces only electron neutrinos. Davis's detector was sensitive only to electron neutrinos. In 1998, the Super Kamiokande experiment in Japan showed that neutrinos can oscillate, changing from one flavor to another as they travel. In 2001, the Sudbury Neutrino Observatory in Canada confirmed that solar neutrinos were indeed oscillating. The total number of neutrinos was exactly right. 2/3 had simply changed flavor during their journey from the Sun to Earth. Raymond Davis shared the 2002 Nobel Prize in Physics for his pioneering neutrino detection work. The solar neutrino problem, once a crisis, became a triumph, confirming both our model of the Sun and the quantum nature of neutrinos. Every second, about 65 billion solar neutrinos pass through every square centimeter of your body, and you feel nothing at all. With fusion ignited and stable, the young Sun settled onto the main sequence, the long, stable middle phase of a star's life. The main sequence is not a place in space. It is a band on the Hertzsprung-Russell diagram, a graph that plots stars by their luminosity and surface temperature. The diagram was developed independently by Ejnar Hertzsprung in 1911 and Henry Norris Russell in 1913. On this diagram, the Sun sits about halfway along the main sequence, a yellow dwarf star spectral type G2V. The letter G indicates its surface temperature, about 5,778 kelvins. The number 2 refines the temperature within the G class. The Roman numeral V means it is a main sequence dwarf, as opposed to a giant or supergiant. The Sun has been on the main sequence for about 4.6 billion years, and will remain there for roughly another 5 billion. During this time, the fundamental balance of the Sun's structure is hydrostatic equilibrium. The outward pressure from nuclear fusion and radiation in the core exactly balances the inward pull of gravity. If fusion increased, the core would expand and cool, slowing the reaction. If fusion decreased, the core would contract and heat up, accelerating the reaction. This negative feedback loop is the Sun's thermostat, keeping it stable for billions of years. The Sun is not static during its main sequence life, however. It is slowly evolving. As hydrogen is converted to helium in the core, the mean molecular weight of the core increases. A heavier core contracts slightly and heats up, increasing the fusion rate. This means the Sun is slowly getting brighter. Today it is about 30% more luminous than it was when it first joined the main sequence. 4 billion years ago, Earth received about 70% of the sunlight it receives today. This raises a puzzle called the faint young sun paradox. How was early Earth warm enough for liquid water when the Sun was so much dimmer? The leading explanation involves a stronger greenhouse effect in Earth's early atmosphere with higher levels of carbon dioxide and possibly methane. The Sun will continue to brighten over the coming billions of years, eventually making Earth too hot for liquid water at the surface. In about 1 billion years, the Sun's increasing luminosity will likely push Earth's surface temperature beyond the point where oceans can survive. Long before the Sun dies, it will make Earth uninhabitable, not through any sudden catastrophe, but through the slow, relentless increase in its brightness. The Sun's radius today is about 696,000 kilometers, roughly 109 times the diameter of Earth. Its mass is about 1.989 times 10 to the 30 kilograms, roughly 333,000 times the mass of Earth. About 73% of the Sun's mass is hydrogen, about 25% is helium, and the remaining 2% is heavier elements. The Sun's surface temperature is about 5,778 kelvins, but its corona, the outermost atmosphere, reaches temperatures of 1 to 3 million kelvins. Why the corona is so much hotter than the surface remains one of the open questions in solar physics. The leading hypotheses involve magnetic reconnection events and the dissipation of magnetohydrodynamic waves. Every 11 years, the Sun's magnetic field reverses polarity, driving a cycle of increased and decreased activity called the solar cycle. During solar maximum, sunspots, solar flares, and coronal mass ejections become more frequent. Sunspots are regions of intense magnetic field that are slightly cooler and darker than the surrounding surface. They were first observed telescopically by Galileo Galilei in 1600, and though Chinese astronomers had noted them with the naked eye centuries earlier. Solar flares release enormous amounts of energy in minutes, equivalent to millions of nuclear weapons detonating simultaneously. Coronal mass ejections hurl billions of tons of magnetized plasma into space, sometimes directly toward Earth. When these reach Earth, they can trigger geomagnetic storms that produce auroras and, in extreme cases, disrupt power grids and satellite communications. The Carrington event of 1859 was the most powerful geomagnetic storm in recorded history, producing auroras visible as far south as the Caribbean. A similar event today could cause widespread technological disruption, but it would not affect the Sun's long-term evolution. These dramatic surface events are minor perturbations in a star whose fundamental nature is calm, steady, and extraordinarily stable. The Sun has been burning hydrogen at a nearly constant rate for longer than complex life has existed on Earth. It will continue to do so for billions of years yet, but the hydrogen in its core is finite and the clock is ticking. Let us look inside the Sun, layer by layer, to understand the machine that has sustained us for so long. At the very center is the core, where fusion occurs. It extends from the center to about 25% of the Sun's radius. The core contains only about 2% of the Sun's volume, but generates 99% of its energy. Surrounding the core is the radiative zone, extending from 25 to about 70% of the Sun's radius. In this zone, energy travels outward as photons, but the plasma is so dense that each photon is absorbed and re-emitted countless times. A photon born in the core takes an estimated 170,000 years to random walk its way through the radiative zone to the surface. The light you see from the Sun today was generated in the core when Homo sapiens had not yet appeared on Earth. Above the radiative zone is the convective zone, the outer 30% of the Sun's radius. Here, energy is carried outward by convection, the physical rising and sinking of hot and cool plasma. Giant convection cells called granules cover the Sun's surface, each about 1,000 kilometers across, lasting about 20 minutes. The visible surface of the Sun is called the photosphere. It is only about 500 kilometers thick, a thin skin on a vast sphere. Above the photosphere is the chromosphere, a thin reddish layer visible during solar eclipses. And above that is the corona, the Sun's outer atmosphere, extending millions of kilometers into space. The solar wind, a continuous stream of charged particles flowing from the corona, fills the entire solar system. It takes the solar wind about 4 days to reach Earth and about a year to reach the outer boundaries of the heliosphere. This entire structure from core to corona is maintained by the steady burn of hydrogen fusion at the center. When that fuel runs out, everything will change. In about 5 billion years, the hydrogen in the Sun's core will be essentially exhausted. The core will be composed almost entirely of helium, the ash of hydrogen fusion. But the temperature will not yet be high enough to fuse helium into heavier elements. Helium fusion requires about 100 million kelvins, far above the current core temperature. Without an energy source at the center, the core will begin to contract under its own gravity. Kelvin-Helmholtz contraction returns. The same mechanism that heated the protostar will now heat the dying core. As the core contracts and heats up, a shell of hydrogen just outside the core reaches fusion temperatures. This hydrogen shell begins to burn furiously, generating more energy than the core ever did during the main sequence. The extra energy pushes the outer layers of the Sun outward. The Sun begins to expand. It is leaving the main sequence. The long, stable prime of its life is ending. The Sun will first become a subgiant star, slightly larger and cooler than it is today. Then it will continue expanding and cooling, climbing up the red giant branch on the Hertzsprung-Russell diagram. Its surface temperature will drop from about 5,800 kelvins to about 13,500 kelvins, shifting its color from yellow-white to deep orange-red. The surface will cool, but the total luminosity will increase enormously because the star is so much larger. This transition from main sequence to red giant takes several 100 million years, a gradual swelling that transforms the Sun utterly. As a red giant, the Sun will be unrecognizable compared to the star we know today. Its radius will grow to about 200 times its current size, roughly the orbit of the inner planets. Mercury will be swallowed. Venus will be swallowed. Earth's fate is less certain but grim. Some models suggest Earth will be engulfed by the expanding Sun. Others suggest it will be pushed outward by the Sun's mass loss. Either way, Earth's surface will be sterilized, its oceans boiled away, its atmosphere stripped, long before the Sun reaches its maximum size. The red giant Sun will be about 2,000 times more luminous than it is today. Its surface will glow a deep reddish-orange, vast and dim per unit area, but enormous in total output. The core, meanwhile, continues to contract and heat. The helium core becomes denser and hotter, approaching the threshold for helium fusion. But something unusual happens in the core of a star like the Sun at this stage. The electrons in the contracting core become degenerate. This is a quantum mechanical effect that occurs when electrons are packed so tightly that the Pauli exclusion principle prevents further compression. In a degenerate gas, pressure depends on density but not on temperature. Normally, a temperature increase would cause expansion, which would cool the gas and regulate the reaction. But in a degenerate core, the temperature can increase without causing expansion. There is no thermostat. This sets the stage for one of the most violent events in the Sun's life, the helium flash. When the core temperature reaches about 100 million kelvins, helium fusion ignites. The reaction is called the triple alpha process because 3 helium-4 nuclei, also called alpha particles, fuse to form carbon-12. First, 2 helium-4 nuclei fuse briefly into an unstable beryllium-8 nucleus, which normally decays in about 10 to the minus 16 seconds. But at the extreme density and temperature of the core, a third helium-4 nucleus collides with the beryllium-8 before it can decay. This 3-body reaction produces stable carbon-12 and a burst of energy. The existence of this resonance in carbon-12 predicted by Fred Hoyle in 1954 was essential for the reaction to occur at a significant rate. Hoyle realized that without this specific nuclear resonance, carbon would be too rare for life to exist, making it one of the most famous anthropic arguments in physics. In the Sun's degenerate core, the helium flash happens suddenly. The fusion reaction begins and releases energy, but the degenerate core does not expand. The temperature rises, which increases the fusion rate, which raises the temperature further in a runaway thermonuclear explosion. The helium flash releases an enormous amount of energy in a matter of seconds, perhaps as much energy as the entire Milky Way galaxy produces in that same instant. But none of this energy reaches the surface. It is entirely absorbed by the overlying layers of the star. The flash lifts the electron degeneracy in the core, allowing it to expand and establish a normal thermostat. After the helium flash, the Sun settles into a new equilibrium, steadily fusing helium in its core and hydrogen in a surrounding shell. It moves to a new position on the Hertzsprung-Russell diagram called the horizontal branch. The Sun will spend roughly 100 million years in this phase, quietly converting helium to carbon and oxygen. On the horizontal branch, the Sun is smaller and hotter than it was at the tip of the red giant branch. It has contracted somewhat, and its surface temperature has increased, but it is still far larger than it was on the main sequence. The core is now fusing helium steadily, producing carbon-12 through the triple alpha process. Some of the carbon captures an additional helium-4 nucleus to form oxygen-16, another key element for life. The proportions of carbon and oxygen produced depend sensitively on the nuclear reaction rates, which have been measured in laboratories here on Earth. Around the helium-burning core, a shell of hydrogen continues to fuse into helium, providing additional energy. This double-burning structure, helium in the core and hydrogen in a shell, is characteristic of horizontal branch stars. The Sun will live in this configuration for about 100 million years before the helium in the core is exhausted in turn. 100 million years sounds like a long time, but compared to the 10 billion years of the main sequence, it is a brief late chapter. The Sun is burning through its fuel faster now because the triple alpha process is less efficient than hydrogen fusion, and the luminosity is much higher. When the helium in the core is exhausted, the Sun enters its final major evolutionary phase, the asymptotic giant branch, often abbreviated AGB. The name comes from the star's position on the Hertzsprung-Russell diagram, where it asymptotically approaches the red giant branch from below. The core is now composed of carbon and oxygen, too cool to ignite carbon fusion in a star of the Sun's mass. Carbon fusion requires temperatures above 600 million kelvins, which the Sun's core will never reach. The carbon-oxygen core contracts and becomes degenerate again, supported by electron degeneracy pressure. Around this inert core, two burning shells alternate, a helium shell and a hydrogen shell. The AGB phase is marked by dramatic instability. The helium shell burns in powerful episodic bursts called thermal pulses. During a thermal pulse, the helium shell ignites in a flash, releasing a surge of energy that briefly pushes the hydrogen shell outward and extinguishes it. The star swells dramatically, then contracts, then swells again, each thermal pulse lasting only a few hundred years. Between pulses, the hydrogen shell reunites and the star settles temporarily before the next pulse builds. These thermal pulses dredge up material from deep inside the star, mixing carbon and heavy elements into the outer layers. This process, called third dredge-up, enriches the star's surface with carbon, sometimes turning it into a carbon star. Carbon stars are some of the reddest objects in the sky, their atmospheres thick with carbon-rich molecules. The AGB phase also produces heavy elements through a process called the slow neutron capture process, or S process. In this process, seed nuclei like ions slowly capture neutrons one at a time, building up heavier elements like strontium, barium, and lead. These elements are carried to the surface by convection and then expelled into space by the star's powerful wind. The Sun on the AGB will lose mass at a prodigious rate, shedding its outer layers in a dense, slow stellar wind. The mass loss rate can reach 10 to the -5 solar masses per year, millions of times the current solar wind. Over the course of the AGB phase, the Sun will lose roughly half of its total mass. This mass does not disappear, it forms a vast expanding shell of gas and dust around the dying star. That shell will become something beautiful. As the Sun ejects its outer layers, the hot core is gradually exposed. The core, now a proto-white dwarf, has a surface temperature that climbs rapidly, reaching 30,000 to over 100,000 kelvins. This intensely hot surface emits powerful ultraviolet radiation that ionizes the surrounding expelled gas. The ionized gas glows, producing one of the most beautiful phenomena in astronomy, a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. William Herschel coined the term in the 1780s because some of these objects look like the disks of planets to his telescope. The Ring Nebula, M57 in the constellation Lyra, is one of the most famous planetary nebulae. Through a telescope, it appears as a delicate ring of glowing gas, about 1 light-year across, surrounding a tiny central star. The Helix Nebula, NGC 7293 in Aquarius, is the closest planetary nebula to Earth, about 700 light-years away. Sometimes called the Eye of God, the Helix Nebula shows intricate structures including cometary knots, dense clumps of gas being sculpted by the central star's radiation. Planetary nebulae come in an astonishing variety of shapes: spheres, rings, butterflies, hourglasses, and complex multipolar structures. The shapes are determined by the star's rotation, magnetic field, binary companions, and the history of its mass loss. The Sun's planetary nebula will likely be relatively simple in shape, perhaps a roughly spherical shell. It will glow for about 10,000 to 20,000 years as the gas expands and thins. Eventually, the gas will become too diffuse to glow and it will merge into the general interstellar medium. The carbon, nitrogen, oxygen, and other elements forged inside the Sun will be returned to the galaxy, available to be incorporated into new stars and planets. Every atom of carbon in your body was once forged in the core of a star like the Sun and expelled in a planetary nebula. You are quite literally made of recycled starlight. The planetary nebula phase is the Sun's farewell gift to the universe, a brief and beautiful display of the elements it created. After the planetary nebula fades, what remains of the Sun is a white dwarf. The white dwarf is the exposed carbon-oxygen core compressed to extraordinary density by gravity. It will have a mass of about 0.5 to 0.6 solar masses, roughly half the Sun's original mass, packed into a sphere about the size of Earth. The density of a white dwarf is about 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5.5 tons on Earth. What supports the white dwarf against further collapse is not heat or fusion. It is a quantum mechanical effect called electron degeneracy pressure. The Pauli exclusion principle states that no two electrons can occupy the same quantum state simultaneously. In a white dwarf, the electrons are packed so tightly that they resist further compression simply because there are no available quantum states for them to be squeezed into. This degeneracy pressure is independent of temperature. A white dwarf could cool to absolute zero and still resist collapse. The physics of degenerate matter was worked out in the 1920s and 1930s by Ralph Fowler and Subrahmanyan Chandrasekhar. Chandrasekhar, working on a ship from India to England in 1930, at the age of 19 calculated the maximum mass a white dwarf could have. He found that if a white dwarf exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure is insufficient to support it. This limit, now called the Chandrasekhar limit, is one of the most important numbers in astrophysics. Above this limit, the star must either shed mass or collapse further, becoming a neutron star or a black hole. The Sun's white dwarf remnant will be well below the Chandrasekhar limit, safely supported by degeneracy pressure for eternity. Chandrasekhar received the Nobel Prize in Physics in 1983 for his theoretical work on the structure and evolution of stars. His work, initially resisted by the eminent astronomer Arthur Eddington, is now universally accepted as correct. The first white dwarf ever identified was Sirius B, the faint companion of Sirius, the brightest star in the night sky. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was wobbling slightly in its position, suggesting an unseen companion. In 1862, Alvin Graham Clark, an American telescope maker, directly observed the companion through one of the finest telescopes of the era. Sirius B turned out to be extraordinarily faint for its gravitational influence, about 10,000 times dimmer than Sirius A. When its surface temperature was measured in 1915 by Walter Adams, it was found to be extremely hot, about 25,000 kelvins. Hot but dim means very small. Sirius B had to be roughly the size of Earth despite having a mass close to that of the Sun. This implied an astonishing density, so extreme that Arthur Eddington initially called as absurd. Adams also measured the gravitational redshift of light from Sirius B in 1925, confirming that its surface gravity was immense. This was one of the earliest confirmations of Einstein's general relativity, time running slower on the surface of a dense star. Sirius B is about 8.6 light-years from Earth. It has been cooling slowly for tens of millions of years. Thousands of white dwarfs have been catalogued since then. They are among the most common endpoints of stellar evolution. About 97% of all stars in the Milky Way will end their lives as white dwarfs, including the Sun. A white dwarf is born hot, with surface temperatures often exceeding 100,000 kelvins. But it has no energy source. No fusion occurs inside it. It shines only from the residual heat stored in its interior. Over billions and trillions of years, the white dwarf slowly radiates this stored thermal energy into space. The cooling process is well understood. The ions in the white dwarf's interior form a crystalline lattice as the temperature drops. Yes, the Sun's final remnant will eventually crystallize. It will become a giant diamond-like crystal in space. The crystallization releases a small amount of latent heat, slightly delaying the cooling process. In 2019, astronomers using data from the Gaia Space Telescope found direct evidence that white dwarfs undergo crystallization. They observed a pileup of white dwarfs at a specific luminosity on the HR diagram, exactly where crystallization theory predicted extra cooling delay. The surface temperature drops from over 100,000 kelvins to about 4,000 kelvins over roughly 10 billion years. Then the cooling slows even further as the temperature difference between the star and its surroundings shrinks. After perhaps 100 billion years, the white dwarf will have cooled below 3,000 kelvins, glowing a faint, dull red. Eventually, over timescales far exceeding the current age of the universe, it will cool to the temperature of the cosmic microwave background. At that point, it will emit no visible light at all. It will become what is sometimes called a black dwarf, a cold, dark, crystallized remnant. No black dwarfs exist yet. The universe is only 13.8 billion years old, not enough time for any white dwarf to have cooled completely. The oldest white dwarfs we observe still have surface temperatures above 3,000 kelvins and are faintly visible. The Sun's white dwarf remnant will take far longer than the current age of the universe to become a black dwarf. In a sense, the Sun will never truly die. Its remnant will persist, cooling imperceptibly, for timescales that dwarf all of cosmic history so far. The Sun's fate as a white dwarf is sealed by its mass. Stars more massive than about 8 solar masses do not become white dwarfs. Their cores are too heavy. They undergo core collapse, producing neutron stars or black holes, often accompanied by a supernova explosion. The Sun, at 1 solar mass, is far below this threshold. It will never explode as a supernova. This is sometimes a disappointment to those hoping for a dramatic end, but the Sun's death will be quiet, gradual, and beautiful. The Chandrasekhar limit of 1.4 solar masses divides the final fates of stellar cores. Below the limit, the core is supported by electron degeneracy pressure and becomes a stable white dwarf. Above the limit, the core collapses further. Electrons are forced into protons to create neutrons, and a neutron star or black hole forms. The Sun's white dwarf will have about 0.54 solar masses, well within the safe range. It will sit quietly in space, a dense crystalline sphere, slowly cooling for eternity. When the Sun dies, what will remain of the solar system? Mercury and Venus will be gone, consumed by the expanding red giant. Earth may survive as a scorched, airless rock orbiting farther out, pushed by the Sun's mass loss to a wider orbit. Mars, the asteroid belt, Jupiter, Saturn, and the outer planets will survive, though their orbits will widen as the Sun loses mass. The Kuiper belt and Oort cloud will remain largely intact, a vast reservoir of icy bodies surrounding the dim remnant. Jupiter's moons, Europa, Ganymede, and Callisto, will cool further. Any subsurface oceans will eventually freeze solid. The solar system will become a cold, dark place, lit only by the fading glow of the white dwarf and the distant stars. The planetary nebula will have long since dissipated, its atoms scattered across interstellar space. Some of those atoms will eventually be incorporated into new molecular clouds, new protostars, new planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these were forged in stars that died before the sun was born. And the elements the sun creates and disperses will one day become part of new worlds, new chemistry, perhaps new life. This is the cosmic recycling program, atoms flowing from star to star across billions of years. The sun's death is just one chapter in the vastly longer story of the universe. The current age of the universe is about 13.8 billion years. The sun will die in about 5 billion years. But the universe will continue for far longer than that. Stars will continue to form for perhaps another 100 trillion years, as long as there is gas available in galaxies. Red dwarf stars, the smallest and most numerous stars, can burn hydrogen for trillions of years. The last red dwarfs will die perhaps 100 trillion years from now, ending the stelliferous era, the age of stars. After the last star dies, the universe enters the degenerate era, dominated by white dwarfs, neutron stars, and black holes. White dwarfs will slowly cool, neutron stars will slowly spin down, black holes will slowly evaporate through Hawking radiation. On timescales of 10 to the 37 years, protons themselves may decay, dissolving ordinary matter entirely. On timescales of 10 to the 100 years, even supermassive black holes will evaporate. Eventually, in the far, far future, the universe will contain only photons, neutrinos, and perhaps a thin soup of electrons and positrons. This is the heat death, the ultimate equilibrium state, where no further work can be done and entropy has reached its maximum. The sun's death is an early event in this incomprehensibly long timeline, a candle blown out in the first minute of a very long night. The sun's fate is typical for a star of its mass, but other stars live and die very differently. A star 10 times the sun's mass burns through its hydrogen in only about 20 million years, roughly 1,000th of the sun's lifetime. Such massive stars end their lives in spectacular supernova explosions, scattering heavy elements across space. The most massive stars, above about 25 solar masses, may collapse directly into black holes. At the other extreme, red dwarf stars with less than half the sun's mass are fully convective, mixing their fuel thoroughly. A red dwarf with 1/10 of the sun's mass can burn hydrogen for over 1 trillion years, far outlasting the sun. Red dwarfs are so long-lived that not a single one has ever died since the universe began. The sun sits in the middle of this range, neither the most dramatic nor the most enduring. It is a perfectly ordinary star, and that is part of what makes its story so compelling. The physics that governs the sun governs every star. The same equations, the same nuclear reactions, the same balance of forces. Understanding the sun is understanding stellar physics itself. We cannot watch the sun's future unfold in real time, but we can observe stars at every stage of the process. Molecular clouds like the Orion Nebula show us the conditions where stars are being born right now. TET Tauri stars in nearby star-forming regions show us what the young sun looked like 4.5 billion years ago. Main sequence stars of type G2V, sun-like stars, are common in the galaxy, and we can study them at various ages. Red giant stars like Aldebaran and Arcturus show us what the sun will look like in 5 to 6 billion years. Aldebaran, in the constellation Taurus, is a red giant about 44 times the sun's diameter, glowing a warm orange. Arcturus, in the constellation Bootes, is also a red giant, about 25 times the sun's diameter. Stars on the asymptotic giant branch, like Mira in the constellation Cetus, show us the pulsating mass-losing phase the sun will enter. Mira is a famous long-period variable star, brightening and dimming over a period of about 332 days as its outer layers pulsate. Planetary nebulae like M57 and the Helix Nebula show us the sun's death shroud, already formed around other stars. And white dwarfs like Sirius B show us the sun's final form, a dense remnant slowly cooling through eternity. By studying these objects, astronomers have pieced together the Sun's entire future biography with remarkable confidence. The Sun is a forge of elements. During its life, it creates helium from hydrogen in its core. Later, on the asymptotic giant branch, it will create carbon and oxygen through the triple alpha process. Through the S process, it will build traces of elements heavier than iron. This process of element creation inside stars is called stellar nucleosynthesis, and it is responsible for most of the elements in the periodic table. The lightest elements, hydrogen and most helium, were made in the Big Bang about 3 minutes after the universe began. Carbon, nitrogen, oxygen, and neon are made primarily in the cores and shells of stars like the Sun. Heavier elements up to iron are forged in the cores of massive stars. Elements heavier than iron are made by neutron capture processes, the S process in AGB stars and the R process in supernovae and neutron star mergers. Fred Hoyle, William Fowler, Margaret and Geoffrey Burbidge published the landmark paper on stellar nucleosynthesis in 1957. Known as the B²FH paper, it explained how almost every element heavier than hydrogen could be synthesized inside stars. Fowler received the Nobel Prize in Physics in 1983, shared with Chandrasekhar, for this work. The Sun contributes modestly to this grand process, creating carbon, oxygen, and trace heavy elements that it disperses into space. A future star may incorporate these atoms into its own planets, completing the cycle of stellar alchemy. The Sun is not just a ball of hot gas, it is a magnetized ball of hot gas, and its magnetic field shapes everything about its behavior. The Sun's magnetic field is generated by a dynamo process deep in the convective zone, where moving plasma creates electric currents. The field emerges through the surface in loops and arches, creating sunspots where the field is strongest. During solar maximum, the surface is covered with spots, prominences, and active regions. During solar minimum, the surface is relatively calm with few or no sunspots. The 11-year solar cycle was discovered by Heinrich Schwabe in 1843 after 17 years of daily sunspot observations. The Maunder minimum, from about 1645 to 1715, was a period when sunspots nearly disappeared. This coincided with the coldest part of the Little Ice Age in Europe, though the connection between solar activity and climate remains debated. As the Sun ages on the main sequence, its rotation slowly decreases due to magnetic braking, and its magnetic activity gradually weakens. By the time the Sun becomes a red giant, its magnetic field will be much weaker, stretched thin by the enormous expansion. The white dwarf remnant may retain a magnetic field. Some white dwarfs have fields of millions of Gauss, but for most the field is weak. The Sun's magnetic personality, so dramatic today, will fade as it ages, like a fiery temperament mellowing with time. We know the Sun's interior structure not by cutting it open, but by listening to its vibrations. The Sun rings like a bell, with millions of acoustic modes vibrating simultaneously. These vibrations, driven by convection, produce subtle oscillations of the Sun's surface with periods of about 5 minutes. The study of these oscillations is called heliosysmology, and it has revealed the Sun's interior structure with remarkable precision. Different acoustic modes penetrate to different depths, allowing astronomers to map the temperature, density, and rotation rate throughout the Sun. Heliosysmology confirmed that the radiative convective boundary lies at about 71% of the Sun's radius. It revealed that the Sun's core rotates slightly faster than its surface, and that the transition between the two occurs in a thin layer called the tachocline. The tachocline is believed to be where the Sun's magnetic dynamo operates. Heliosysmology also confirmed the sound speed profile inside the Sun, matching the standard solar model to within a fraction of a percent. This technique has been extended to other stars where it is called asterosysmology, revealing the internal structures of distant suns. The Sun exhales a continuous stream of charged particles called the solar wind. The solar wind flows outward at speeds of 300 to 800 km per second, carrying magnetic field lines with it. This wind inflates a vast bubble around the Sun called the heliosphere, which extends far beyond the orbit of Pluto. The boundary where the solar wind meets the interstellar medium is called the heliopause. In 2012, Voyager 1 crossed the heliopause, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, confirming the measurements at a different location. The heliosphere protects the solar system from some of the galactic cosmic rays that permeate interstellar space. As the Sun evolves into a red giant, its wind will strengthen enormously, expanding the heliosphere temporarily. But after the planetary nebula phase, the white dwarf's feeble wind will create only a tiny heliosphere, if any. The solar system will lose its protective bubble and be exposed directly to the interstellar medium. Let us consider what will happen to Earth as the Sun ages. In about 1 billion years, the Sun's luminosity will increase by roughly 10%. This will trigger a moist greenhouse effect on Earth, trapping water vapor in the upper atmosphere where ultraviolet radiation breaks it apart. Hydrogen will escape to space, and over millions of years, Earth's oceans will slowly evaporate. In about 1.5 billion years, the surface temperature will exceed the limit for any known life form. In about 3 to 4 billion years, Earth's surface will resemble Venus today, with a thick carbon dioxide atmosphere and surface temperatures above 400 degrees Celsius. When the Sun becomes a red giant in about 5 billion years, Earth's remaining atmosphere will be stripped away entirely. The surface will be baked to thousands of degrees, melting rock and erasing all trace of the world we know. Whether Earth is physically consumed by the expanding Sun depends on the details of the Sun's mass loss and Earth's orbital evolution. Current models suggest Earth has roughly a 50-50 chance of surviving inside the red giant's envelope. Even if Earth survives, it will be an airless, scorched cinder orbiting a white dwarf. The beautiful blue marble will be gone, replaced by a world as dead and barren as the Moon. This is not a cause for despair tonight. It is a cause for wonder that we exist at all in this brief window of habitability. White dwarf physics is one of the great achievements of 20th century astrophysics. The mass-radius relation for white dwarfs is counterintuitive. More massive white dwarfs are smaller, not larger. This is because greater mass means stronger gravity, which compresses the degenerate electrons more tightly. A white dwarf of 1.2 solar masses is actually smaller than one of 0.5 solar masses. This inverse relationship is a direct consequence of quantum mechanics and was derived by Chandrasekhar. White dwarfs are composed primarily of carbon and oxygen, with a thin atmosphere of hydrogen or helium. The atmosphere is extremely thin, less than 1% of the star's radius, but it is all we can see from the outside. White dwarfs are classified spectroscopically. DA white dwarfs show hydrogen absorption lines, Db show helium. About 80% of known white dwarfs are DA type, with hydrogen-dominated atmospheres. Some white dwarfs show traces of heavier elements in their atmospheres, metals that should have sunk below the surface long ago. The presence of these metals suggests that asteroids or small planets are still falling onto the white dwarf, polluting its atmosphere. This debris disk phenomenon provides a window into the composition of extrasolar asteroids and planetesimals. The Sun's white dwarf may one day accrete remnants of its own former asteroid belt, carrying memories of the solar system's youth. Not all white dwarfs fade quietly. Some meet a spectacular end. If a white dwarf orbits closely with another star, it can gravitationally pull material from its companion onto its surface. If enough material accumulates, the surface hydrogen can ignite in a thermonuclear explosion called a nova. A nova brightens the white dwarf by a factor of 1 million or more, then fades over weeks to months. The white dwarf survives the nova and can repeat the process over thousands of years. But if the accreted material pushes the white dwarf's total mass above the Chandrasekhar limit, something far more dramatic happens. The entire white dwarf is consumed in a thermonuclear explosion called a Type YR supernova. Type YR supernovae are among the most energetic events in the universe, briefly outshining an entire galaxy. They are also remarkably uniform in brightness, which makes them invaluable as standard candles for measuring cosmic distances. It was the study of Type 1r supernovae in distant galaxies that led to the discovery of the accelerating expansion of the universe in 1998. That discovery earned the Nobel Prize in Physics in 2011 for Saul Perlmutter, Brian Schmidt, and Adam Rice. The Sun, being a single star, will never experience a nova or a Type Ia supernova. Its white dwarf will simply cool in solitude. Let us review the Sun's entire life in a single calm summary. About 4.6 billion years ago, a molecular cloud collapsed and the Sun was born as a protostar. It spent about 100,000 years as a protostar, heating through gravitational contraction. Then about 10 million years as a TTRE star, a turbulent stellar toddler. At 4.6 billion years ago, hydrogen fusion ignited and the Sun joined the main sequence. It has been on the main sequence for 4.6 billion years and will remain for about 5 billion more. In about 5 billion years, hydrogen in the core will be exhausted and the Sun will begin expanding. Over several hundred million years, it will swell into a red giant, engulfing the inner planets. The helium flash will ignite helium fusion in the core, and the Sun will settle onto the horizontal branch for about 100 million years. When helium is exhausted, the Sun enters the asymptotic giant branch, pulsating and shedding its outer layers. A planetary nebula forms and glows for about 10,000 to 20,000 years. The remaining core, a white dwarf of about 0.54 solar masses, cools slowly for eternity. Total active lifetime from protostar to planetary nebula, roughly 12.5 billion years. Total cooling time as a white dwarf, trillions upon trillions of years. The Sun spends most of its existence not as a blazing star, but as a quiet cooling ember. The Sun belongs to a generation of stars called Population I, metal-rich stars found in the disk of the Milky Way. Population I stars contain elements heavier than helium, elements synthesized and dispersed by previous generations of stars. An earlier generation, Population II, consists of older metal-poor stars found in the galactic halo and globular clusters. Population IIn stars formed from gas that had been enriched by only a few rounds of stellar nucleosynthesis. The very first stars, hypothetical Population III, formed from the pristine hydrogen and helium of the Big Bang. Population III stars are thought to have been extremely massive, hundreds of times the Sun's mass, and very short-lived. No Population III star has ever been directly observed. They all died billions of years ago. The Sun inherited the chemical legacy of multiple generations of stars, each contributing elements forged in their cores. Our Sun is a third or fourth generation star, born from the recycled ashes of stars that lived and died long before it. Every atom in the Sun heavier than hydrogen and helium has a story, a history of being forged in another star's fire. The Sun has been the ultimate energy source for life on Earth for as long as life has existed. Photosynthesis, the process by which plants convert sunlight into chemical energy, has powered the biosphere for over 2 billion years. Fossil fuels are stored sunlight, ancient photosynthetic organisms compressed and transformed over millions of years. Wind is driven by differential solar heating of the atmosphere. Rain is driven by solar evaporation of the oceans. Almost every source of energy on Earth, with the exception of nuclear power and geothermal energy, traces back to the Sun. The Sun's steady output over billions of years provided the stable environment needed for complex life to evolve. If the Sun had been significantly more variable, life might never have gained a foothold. The habitable zone, the range of distances where liquid water can exist on a planet's surface, is defined by the star's luminosity. Earth sits comfortably within the Sun's habitable zone today, though it will drift out as the Sun brightens. The window of habitability for Earth is limited. We exist in the middle of it, not at the beginning or the end. The Sun gave us life, and the Sun, in its slow aging, will eventually take the conditions for life away. This is not cruelty, it is physics, and there is a quiet grandeur in it. Humanity has studied the Sun with increasingly sophisticated instruments for centuries. Galileo's telescope observations of sunspots in 1610 began the era of solar astronomy. Spectroscopy in the 19th century revealed the Sun's chemical composition, including the discovery of helium. Helium was first detected in the Sun's spectrum during the 1868 solar eclipse before it was found on Earth. The element is named after Helios, the Greek god of the Sun. In the space age, missions like the Solar and Heliospheric Observatory, SOHO, launched in 1995, have monitored the Sun continuously. The Solar Dynamics Observatory, SDO, launched in 2010, captures images of the Sun every 12 seconds in multiple wavelengths. NASA's Parker Solar Probe, launched in 2018, has flown closer to the Sun than any previous spacecraft. It has passed within about 6 million kilometers of the Sun's surface, sampling the solar wind and corona directly. These missions are helping us understand the detailed mechanisms of solar activity, the corona heating problem, and the solar wind. We know more about the Sun today than at any point in human history, and that knowledge continues to grow. But we already know the Sun's fate. The physics is settled. The only question is the details of timing and evolution. There is something deeply moving about the idea that the Sun will die. It has been the most constant presence in every human life, rising each morning, warming each afternoon, setting each evening. Every civilization has worshipped it, studied it, or told stories about it. The Egyptian god Ra crossed the sky each day in a solar bark. The Aztec Tonatiuh demanded sustenance to keep shining. The Greeks told of Helios driving a golden chariot from east to west. Today we know the Sun is not a god, but a natural thermonuclear reactor, and somehow that makes it more wondrous, not less. To know that this ball of plasma, 1.3 million times the volume of Earth, sustains itself through quantum tunneling and nuclear physics is astounding. And to know that it will one day shed its outer layers in a glowing nebula and settle into quiet crystalline death is profoundly beautiful. Stars are born, they live and they die, scattering their elements into the cosmos to be reborn in new forms. The Sun is part of this great cycle. We are part of this great cycle. Every atom in your body was forged in a star that died before the Sun was born. And when the Sun dies, its atoms will join the interstellar medium, available for new stars, new planets, new possibilities. The equations that describe the Sun's evolution are among the most beautiful in physics. The equation of hydrostatic equilibrium tells us how pressure supports the star against gravity. The equation of radiative transfer describes how photons carry energy outward through the dense plasma. The equation of energy generation describes how nuclear reactions produce power in the core. And the equation of mass conservation accounts for every kilogram of material in the star. Together, these four equations formed the system of stellar structure equations, first formulated by Arthur Eddington in the 1920s. Solving them requires numerical computation, and modern stellar evolution codes can track a star from birth to death in exquisite detail. The MESA code, Modules for Experiments in Stellar Astrophysics, is one of the most widely used tools for this purpose. With MESA, researchers can model the Sun's evolution from the zero-age main sequence through the red giant phase to the white dwarf. The predictions match observations of stars at every stage, giving us high confidence in the Sun's predicted future. The quiet mathematics of stellar evolution is one of the great triumphs of theoretical astrophysics. Let's return to the proton-proton chain for a moment, because its details are exquisitely beautiful. The rate-limiting step is the very first 1-2 protons fusing into deuterium. This step requires one of the protons to undergo inverse beta decay, turning into a neutron via the weak nuclear force. The weak force is extraordinarily feeble compared to the strong force. This is why the reaction is so slow. An average proton in the Sun's core will bounce around for about 1 billion years before successfully fusing with another proton. The Sun is not a raging furnace. It produces energy at a rate of about 276 watts per cubic meter in its core. That is less than the metabolic rate of a human body. The Sun shines because it is enormous, not because its fuel is burning rapidly. Each cubic meter of your body produces more heat than a cubic meter of the Sun's core. The Sun's power comes from the sheer volume of its core, trillions of cubic meters all contributing their tiny share, There is a gentle lesson here. Enormous power can emerge from countless small contributions sustained over vast time. The CNO cycle is the other major hydrogen fusion pathway in stars. It uses carbon-12, nitrogen, and oxygen as catalysts, cycling through a series of reactions that ultimately produce helium-4 from hydrogen. The cycle begins with a carbon-12 nucleus capturing a proton to form nitrogen-13. Nitrogen-13, unstable, undergoes beta plus decay to become carbon-13, emitting a positron and a neutrino. Carbon-13 captures another proton to become nitrogen-14, the most abundant product of the CNO cycle. Nitrogen-14 captures yet another proton to form oxygen-15. Oxygen-15 decays to nitrogen-15, and finally nitrogen-15 captures a proton and splits into helium-4 and carbon-12, completing the cycle. The carbon-12 is regenerated at the end, acting as a true catalyst that is not consumed. In the Sun, the CNO cycle contributes only about 1.7% of the total luminosity. But in stars just 50% more massive than the Sun, the CNO cycle dominates because it is much more sensitive to temperature. The transition from pp chain dominance to CNO cycle dominance occurs at core temperatures around 17 million kelvins. This temperature sensitivity shapes the internal structure of stars, determining whether they have convective or radiative cores. The red giant branch is not a single state, but a continuous evolutionary trek. As the Sun ascends the red giant branch, its luminosity increases steadily, while its surface temperature decreases. The hydrogen-burning shell surrounding the helium core drives this expansion. The first dredge-up occurs early on the red giant branch, when the deepening convective envelope reaches layers that have been processed by nuclear burning. This brings products of hydrogen burning, including helium and carbon-13, to the surface for the first time. Spectroscopic observations of red giant surfaces confirm these composition changes, validating our models of stellar interiors. The tip of the red giant branch is reached when the helium core mass reaches about 0.45 solar masses. At this point, the core temperature reaches 100 million kelvins, and the helium flash occurs. The luminosity at the tip of the red giant branch is about 2,000 times the Sun's current luminosity. The tip of the red giant branch luminosity is so consistent across stars that it is used as a distance indicator in astronomy. By measuring the apparent brightness of the brightest red giants in a galaxy, astronomers can estimate how far away that galaxy is. Thermal pulses on the asymptotic giant branch are among the most dramatic events in the Sun's future. Each thermal pulse is triggered by a thin shell of helium accumulating between the hydrogen-burning shell and the carbon-oxygen core. When the helium shell reaches a critical mass, it ignites in a helium shell flash. The flash releases enormous energy over a few hundred years, briefly increasing the luminosity of the helium shell by a factor of 1,000,000. This energy pushes the outer layers outward and temporarily extinguishes the hydrogen shell. The intershell region between the two shells is mixed by convection during the flash, dredging up carbon and process elements. After the flash subsides, the star contracts and the hydrogen shell reignites, beginning the cycle again. The interval between thermal pulses is typically about 100,000 years for a star of the Sun's mass. Each pulse becomes stronger than the last, and the mass loss rate increases with each cycle. Eventually, the mass loss becomes so intense that the remaining hydrogen envelope is stripped away entirely, ending the AGB phase. This final ejection of the envelope is what creates the planetary nebula. The thermal pulse cycle is a dying star's heartbeat, each pulse weaker and more desperate than the last. As a white dwarf cools below about 6,000 kelvins in its interior, the carbon and oxygen ions begin to crystallize. The ions arrange themselves into a regular lattice, most likely a body-centered cubic structure. This crystallization releases latent heat, which temporarily slows the cooling of the white dwarf. The Gaia Space Telescope observed this cooling delay as a pileup of white dwarfs at a specific luminosity. As the crystal grows, heavier oxygen ions sink toward the center and lighter carbon ions float upward. This gravitational settling releases additional energy, further delaying the cooling. The crystallization process begins in the center and slowly extends outward as the temperature drops. Over billions of years, the entire white dwarf becomes a solid crystal, a giant jewel floating in space. In 2004, astronomers proposed that the white dwarf BPM 379.3 had largely crystallized and nicknamed it Lucy after the Beatles' song Lucy in the Sky with Diamonds. The idea of a diamond star is poetically beautiful but physically accurate. The carbon lattice in a white dwarf is indeed similar to diamond. The Sun's ultimate fate is to become a slowly dimming crystal sphere, drifting through the darkness for eternity. We have walked through the entire life of the Sun tonight, from cold gas to cooling crystal. It was born in a molecular cloud, heated by gravity and ignited by quantum tunneling. For nearly 10 billion years, it burns hydrogen in its core, a steady thermonuclear reactor balanced by its own gravity. When the hydrogen runs out, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf. The white dwarf cools and crystallizes over timescales that make the current age of the universe seem brief. None of this is speculation. Every stage has been observed in other stars, measured, modeled, and confirmed. The Sun will die, that is certain, but its death will be quiet, beautiful, and productive. The elements it forges, carbon, oxygen, traces of heavier atoms, will be returned to the galaxy. New stars will form from those atoms, new planets, perhaps new life. The Sun is not eternal, but its legacy is woven into the fabric of future worlds. Right now, as you lie in the dark, the Sun is below the horizon, fusing hydrogen at the same steady rate it has maintained for billions of years. It will rise again tomorrow, as it has every day of your life, and every day for the past 4.5 billion years. It will continue to rise for billions of years to come, though no human eyes may be there to see it. Let that thought carry you gently into sleep. The Sun is burning, the Sun is aging, the Sun is aging, and the Sun will die. But not tonight, not for 5 billion years. Tonight the Sun is resting just below the curve of the Earth, and so are you. Sleep well, knowing that the star that gave you life is still burning steady and calm in the quiet dark. Good night. The 5-minute oscillations of the Sun were first detected in 1960 by Robert Layton at the Mount Wilson Observatory. Layton initially thought the oscillations were localized surface phenomena, not global vibrations. In the early 1970s, Roger Ulrich and John Liebacher independently proposed that the oscillations were acoustic standing waves. These waves bounce back and forth inside the Sun, reflected at the surface and refracted by the increasing temperature with depth. Each mode of oscillation probes a different depth, giving astronomers a three-dimensional map of the Sun's interior. By 1975, Franz Steubner had confirmed the theoretical predictions observationally, establishing Helios's homology as a field. The SOHECHO spacecraft and the ground-based networks GONG and BISON have continuously monitored solar oscillations for decades. These observations have confirmed the standard solar model to extraordinary precision. They have also revealed subtleties like the sharp transition at the tachocline and slight variations in the sound speed profile. Helios's homology is essentially an ultrasound of a star, and it works beautifully. How do we know the Sun's chemical composition so precisely? Part of the answer comes from spectroscopy, analyzing the wavelengths of light absorbed and emitted by the Sun's atmosphere. But another crucial source of information is meteorites, specifically a class called CI chondrites. CI chondrites are the most primitive meteorites, their composition essentially unchanged since the solar system formed. For elements that are not volatile, the composition of CI chondrites matches the Sun's photospheric composition remarkably well. This agreement confirms that both the Sun and the meteorites formed from the same primordial material. The Solar Abundance Table, listing the relative amounts of every element in the Sun, is a fundamental reference in all of astrophysics. Hydrogen accounts for about 91% of the Sun's atoms. Helium accounts for about 9%. Everything else, all the carbon, oxygen, iron, silicon, every element that makes up Earth and life, is that remaining fraction of a percent. The universe is overwhelmingly made of the two simplest elements. Everything else is a trace impurity. To appreciate the Sun's mortality, consider the red dwarfs. Proxima Centauri, the nearest star to the Sun, is a red dwarf with about 12% of the Sun's mass. It burns hydrogen so slowly that it will remain on the main sequence for about 4 trillion years. The Sun will have been dead for trillions of years before Proxima Centauri even begins to evolve. Red dwarfs are fully convective, meaning they can mix all their hydrogen fuel into the core, wasting nothing. The Sun, by contrast, can only fuse the hydrogen in its core, about the inner 10% of its mass. If the Sun could access all its hydrogen, it would live for over 100 billion years instead of 10 billion. Red dwarfs will never become red giants. They will slowly transition from red to blue as they exhaust their fuel, then fade as helium-white dwarfs. But this process takes so long that it has never happened anywhere in the observable universe. The Sun lives a full, dramatic life and dies. Red dwarfs just keep going, steady and dim, outlasting everything around them. The final composition of the Sun's white dwarf core depends on the details of helium burning. The triple alpha process produces carbon-12, and some of that carbon captures an additional helium-4 to produce oxygen-16. The ratio of carbon to oxygen in the final white dwarf depends on the rate of the carbon-12 plus alpha reaction. This reaction rate has been measured in laboratories, but uncertainties remain, making the exact C/O ratio one of the open questions in stellar physics. Current models suggest the Sun's white dwarf will be roughly 50% carbon and 50% oxygen by mass. A thin layer of helium surrounds the carbon-oxygen core, and an even thinner layer of hydrogen sits on top. These layers are incredibly thin compared to the star's radius, like paint on a bowling ball. The carbon-oxygen core is where the crystal will eventually form, a lattice of carbon and oxygen ions in a sea of degenerate electrons. It is a strange and beautiful final state, a quantum mechanical crystal the size of Earth. The white dwarf Sun will have strong enough surface gravity to produce measurable gravitational redshift. Light escaping from the surface of a white dwarf loses energy climbing out of the deep gravitational well. This redshift was first measured for Sirius B by Walter Adams in 1925. The redshift is about 80 km per second equivalent, easily measurable with modern spectrographs. This measurement confirmed two things simultaneously, that white dwarfs are extraordinarily dense and that Einstein's general relativity is correct. Every white dwarf observation is a test of both quantum mechanics and general relativity working together. Time runs measurably slower on the surface of a white dwarf than in the space around it. A clock on the Sun's white dwarf surface would lose about 60 seconds per year compared to a distant clock. This is tiny compared to a neutron star, but it is a real, measured effect of curved spacetime. Degenerate matter is one of the most exotic states in the universe. In normal matter, atoms have electrons in distinct orbits, and there is plenty of space between them. In a white dwarf, the matter is so compressed that the electrons are no longer bound to individual atoms. Instead, the electrons form a quantum gas, filling every available energy state from the lowest up. This is called a Fermi gas, named after Enrico Fermi. The pressure of this electron gas is what supports the white dwarf against collapse. The key insight is that this pressure does not depend on temperature, it is purely a quantum mechanical effect. Even at absolute zero, the electrons would still exert degeneracy pressure because they cannot all be in the lowest energy state. This is the Pauli exclusion principle at work on a stellar scale. At extremely high densities, the electrons become relativistic, moving at speeds approaching the speed of light. Relativistic degeneracy, pressure increases more slowly with density than non-relativistic degeneracy pressure. This is why there is a maximum mass for a white dwarf. Above the Chandrasekhar limit, even relativistic electron degeneracy pressure fails. The Sun will die, and now you know how. Not in a sudden explosion, not in a violent collapse, but in a slow, graceful unwinding of nuclear fuel. It will swell, shed its skin of gas and dust, and retreat into a small, dense, crystalline remnant. The planetary nebula it leaves behind will be one last bloom of colour in the darkness. The white dwarf will cool through temperatures no human will ever measure, over time scales no human will ever witness. But the atoms it forged, the carbon and oxygen it created from nothing but hydrogen, those atoms will live on. They will drift through the galaxy, join new clouds, form new stars, perhaps land on new worlds. The sun is mortal, but its elements are eternal, recycled endlessly in the great furnace of the cosmos. You are made of these elements. You are part of this cycle. You are stardust, contemplating the star that gave you form. There is deep peace in this thought. Nothing is wasted. Nothing is lost. Everything is transformed. The sun will die. The atoms will endure. And the universe will go on, patient and vast, long after the last white dwarf goes dark. Sleep now. Let the calm mathematics of stellar evolution carry you into rest. The sun is burning gently in the dark, as it has for 4.5 billion years. Tomorrow it will rise again. Tonight it